Good crowd tonight. It's awesome. So this is lesson 3. We got about 14 class sessions. So we can start. I always like it when we get up to a certain multiple where I can figure out what percentage of the class we are. Not in my head. We're on lesson 3, but we're going to be continuing to explain topics that are in chapter 2. I don't want to rush past the fundamentals and blow everybody away. I want to make sure everybody gets grounded really well in how to do this stuff before speed picks up. I think I mentioned at the beginning that this is a different textbook than we've been using previously. And so as I'm getting into the later chapters and stuff, they jump into the programming logic pretty darn quickly. And when we get to chapter 3, we'll probably spend more than one class session on chapter 3 also, like we are on chapter 2. Take it easy and make sure we go at a measured pace here. So hopefully that makes some of you feel better. But if you're bored, come see me. I'm sure I can come up with something fun for you to play with. So today, if you're looking through chapter 2, you probably notice that there's some things that we didn't really cover last time. But this time, the topics on the screen there that you see, that's what we'll be covering. What is a literal in Python? There's data types. When we start learning a programming language, we have to discuss how memory is handled, how you store values, how you use those values and expressions to calculate other values, and etc. And so we'll go through that stuff, the finer details of that. There's a lot of terminology in programming. And if you think the terminology is bad, wait till you get a job and start learning the 3-letter acronyms that go with whatever particular job you've got. That's fun too. But one of those is type inference. We're basically, or the compiler is inferring what data type a variable is based on the context. And so we'll talk about how that works in Python and a little bit from other languages peppered in there. Variables, constants, declaring, lots and lots of stuff. And then some more of the details about input and output as we go through there. I've talked to a couple of you outside of class, and it's like I have to strike this balance between introducing things that we haven't talked about yet, and introducing a little bit of mild confusion is intentional in some cases in order to either make you go look it up yourself and learn how to do that, or so that when I do get to a point where I explain it and fill in the blanks for you, it's like, oh, that's what he was talking about. It kind of makes a connection in your brain. So that's, maybe some other teachers don't do that, but that's my style. I feel like that's the best way to learn this stuff is to be mildly confused and then figure it out and have that aha moment. For different people, that aha moment, oh, I see what we're doing, comes at different stages, in the first several classes. So if you're still a little confused about some of these things, it's perfectly normal at this point. Just want you to do what I do, follow the leader for a little bit until it starts to click. So moving on. So when we talk about literals, so I mean, literally, the value 17. So when I say 17 digits 17 of the compiler, I literally mean that value. It's not symbolic for anything. It's not a name for some location in memory or something abstract. It's literally the number 17. And that's all we mean by that. Anytime you see, something in double quotes, that's a literal string value, or a number, a whole number, a decimal number. Those are literal values that we're using in our code. That's what we're talking about. Sometimes they refer to them as constant literals, or constants. I just prefer to refer to them as literals because that's what they are. We might also use the term immutable, throw that out there. Immutable, we'll talk about that some more, but immutable just means it doesn't change. I can't assign 17 the value of 16. No, it's always going to be 17 every time you see those symbols. Okay, so we mentioned some of this, the difference between programming and math. So in math, you see equations, every shape and size, calculus, trigonometry, whatever, you see lots and lots of equations, equalities set up. And that's not what we do in programming. So when I talk about an assignment statement, it's always going to be a variable name on the left, something whose value I can modify, equals is the assignment operator in that case, and then an expression on the right side. Now that expression can be made up of literals, literal numbers or string values, or other variables, and usually in combination with operators. So plus, minus, times, divide, those are operators. And so, we might have function calls, but it's going to be a combination of a bunch of stuff like that that forms an expression that I can evaluate and get a value from it, and then take that value and assign it to the variable that's on the left side. So that first one, I would say, take the string literals MA and RK and concatenate them together, which is what the plus operator means with strings. It means concatenation, and assign the resulting string to the variable first name. That's how you would read that. Okay, any questions there? The programs that we've been doing that kind of stuff. Hopefully I'm just putting names to it and not introducing something brand new. Here's some other literals that Python supports. They all look kind of funny, but if you want to type in a hexadecimal literal, you start it with a 0x, and then whatever hexadecimal characters, 0 through 9, A through F that you want. Binary, you can say 0b. You can type in, Python's pretty cool and unique in this regard. You can actually use that exponential notation and it'll know what you're talking about. You want to type in mathematical values, which comes in real handy because we've mentioned before that data mining folks like to use Python. And if they're talking about numbers that are in exponential format, it makes it really convenient for them to type in the literals that they need to use. Character data. Now, character data can be kind of confusing sometimes. You see people getting confused with the single quotes and the double quotes. They're basically equivalent, and they do it that way because sometimes you want, like the example down there at the bottom, the true statements, Mark is a cool dude, with double quotes on the outside and single quotes in the middle, versus single quotes on the outside and double quotes in the middle. That's so that you can include a single quote or a double quote inside your string if you need to. Okay, so knock yourself out.
Wait, 2 quotes is to make the string, and 1 quote is to make the string instead of string?
They're both strings. They're interchangeable. But yeah, if you wanted to put something in quotes inside a string, then just surround it with single quotes so you can use the double quotes in the middle. Likewise, you can,
All right,
the vice versa is true. Okay, so then the next question, double quote H double quote. Is that a character or a string like single quote H single quote? Pretty much the same. Is double quote 9 the same as just the numeric literal 9? No. Right? I can concatenate things to the character 9, but I would add things to the value 9. The operators work differently on those 2 data types. And then same thing, is double quote false similar to false? No. Similarly, the latter, the false without the quotes, is a literal Boolean true or false value. True or false, yes or no, etc. So that's literals. Okay, so a variable. A variable is just a name for a spot in memory that holds a value. We can say that over and over and over again, but that's all that it is. So there's a bunch of memory out there. We're picking one spot, or the compiler picks a spot, and we're giving it a name. So anytime we use that name, we want what's ever stored at that location in memory. That's all it is.
How will you make a variable inside of Python?
We will see that.
Oh, okay.
So in Python, variables are mutable, which means, we talked about immutable being they can't change. So mutable means they're changeable. I can store one value in it, and a couple of lines later, I can change it, store a different value in it. And if we want to see what's in it, we have to evaluate it. We have to add it to an expression and use it in some context. Yeah. In other languages, so I would call Python a loosely typed or not a strongly typed programming language, because the type is associated with what data is stored in the variable. It's not a part of the variable declaration itself. Languages like C++, if you declare an integer variable, you're not allowed to put a string in it. If you try to do that, it's going to give you an error saying you're trying to put the wrong type of data into the variable that you told me was for integers. So the type is part of the declaration in those other languages. In Python, the type is part of the data that's stored there. Okay, it's a big difference. And as some of my Java students can attest, it's kind of crazy in your head when you've been, through a semester of Python and it's loosely typed to go to a language where it's strongly typed and have to adjust your mindset to have to declare your variables and all that. So here's a screen. I apologize for the size there. We'll do some of this on the screen too, though. In fact, maybe I can just do that instead of because if I just bring one up, I can make it as big as I want it. Is that a little bit better?
Yes.
Okay. So if Python comes on Windows machines now, and you can, it's not something special that they had to install. If you just open up a command prompt like I did and just type Python, then it runs Python and you can start issuing commands. So I can create an expression like 17 and hit enter, and it just repeats 17 back to me. Not very useful, but it worked. But what if I want to know what data type that literal is? I can use a function called type and type in the expression 17, and it will tell me, oh, that's an integer. Well, how did it know that it was an integer? We'll talk about this, but it's type inference. Based on what the value is that I'm typing in there, Python is inferring what data type it should be. So it's 2-digit number, doesn't have any decimal, doesn't have double quotes around it. Okay, I'm going to assume this is an integer. Likewise, if I said type 3.1415, it's going to say I'm going to infer that that's a type float. Just does that automatically for me. It does that because it needs to know, in order to do it, when I start doing operators and operating on these literals, it needs to know what type it is because it has different rules for different types of things. Like we saw, if I say 17 plus 34, I get 1734. It concatenated it because it inferred that those were strings and it crunched them together. It didn't add them, right? Different rules for different stuff. What about something like true or false? If I use the type function and I just type the word true, it says, ooh, that's a class bool. So that's a whole different thing. It's not integer, it's not string, it's a Boolean. What else is in my list here? Oh yeah, I like this one. Type 4.95 E plus 8. If I try to get what data type that is, it says it's a float. Excellent. There's other stuff later. I'm not going to go into this too much, but if you use the square brackets, that's how we create a list.
Oh, yeah.
And I can, show you how that works. If I say X equals I just created a list and put a bunch of values in it. So the square brackets is a list. So if I say type X, what is X? X is a list. You know how that works? And then similarly, there's a thing called a dictionary that we'll talk about later. It's essentially a list, but it's a key and a value pair collection. You use it for lookup values. So if I have a customer ID as the key and the first and last name is the value, that's a dictionary. So anyway, there's lots and lots of stuff, lots of data types, lots of types of objects. And if I want to know what type they are or what Python's going to infer that they are, I can use this type function. How about type of 5 divided by 4? Oh, that's interesting. 5 and 4 are both integers. So why did that tell me that that's a float?
It's the answer.
Hmm?
Because the answer is missing.
Yeah, so is that good or bad? Do I want Python upgrading it to a float whenever I do a divide? How about type 5 times 4? See, that stays an integer. But whenever I do a division, it converts it to a float. I can get more complicated with it. What type is 5 times 4 divided by 2? What do you think that's going to be?
Integer.
Oh,
Integer.
we have disagreement in the crowd. Yeah, so it evaluates the whole expression. 5 times 4 is 20, divided by 2 is 10, but it's a float because we had the division in there as part of it. So as soon as it hit the division operation, it converted it up to a float. Maybe we want to do that, maybe we don't, but that's what Python does. It thinks it's being nice to us. It says, oh, you're doing division. We probably should add some decimal positions in there. Yeah.
What's a float?
Okay, float's just decimal. We'll get to that in a couple of slides. I'm just getting ahead of myself. But float just means it's got a decimal point value. I think I did one of those earlier, but type 5.429, some kind of a decimal value, then Python looks at that decimal value and says, oh, that's a float. So we'll get to that.
Right.
I'll stop playing. Okay, so another thing about variables is we have naming rules. There's things that we can use as a variable name. Again, a variable is just a name for a location in memory that holds a value, right? So there's legal and illegal. And then there's the common way that we name variables. And this is going to vary greatly depending on who you talk to. Some people will religiously say, no, this is the right way to name variables. You have to do it that way. Other people are like, I've worked at a bunch of different places and this place did it this way and that place did it that way. It's just a convention. You have to get a job first. And as soon as they start, giving you a paycheck and starts going into your bank account, then they can tell you what your variable naming convention should be. Okay, great. First thing is, well, obviously, if there's a variable already created that exists, then it already exists. You can't use variable name for a new variable for
Thank you.
one that already exists. That makes sense. It either has to start with a letter, can be uppercase or lowercase, or it can start with an underscore character. Can't start with a number. So if you see on a quiz, which of these is a valid variable name and it starts with a number, no, that one's not valid. And then there's all these uppercase, lowercase conventions that you'll see, and they've got names. So you kind of need to associate the name to how the casing happens. So camel case, it starts out lowercase, and then the first letter of each word after that is uppercase. So it kind of looks like a camel, so they call it camel casing. Snake casing, I guess it's because of the little underscore drags on the ground, so they call it snake casing. You'll see snake casing in uppercase, like we were talking before. You can use that for constants if we had constants. And like my point says, don't get religious about it. It's not important. It doesn't make your code any faster or slower. The religious arguments around naming convention usually are whether it's more readable to do it one way or the other. And that's just an opinion. Different people have different opinions on it. So this is what I was mentioning earlier. Some languages are type safe languages. You know, is it good or bad? Again, it's one of those things. As long as you know the rules and you can play within the rules, it's fine. The harder thing is switching from one set of rules to the other and remembering what you're doing when you develop the habits and the muscle memory with one language. So I kind of already said this, so I'm going to go pretty quickly. Python is what we call a dynamically typed language instead of a type safe language. Yeah, so each assignment statement I can say my bear equals 17. What type is it? It's an int. Then I can turn right around and say my variable equals a string. And now it's a string. So the type and the value can change from assignment statement to assignment statement is all that means. What I'm doing there using that type function, some dynamically typed languages let you ask about the variable, like with that type function that I'm using. Others, like if it's a type safe language, why would you need to ask what type of data the variable is? It's always what you declared it to be. If you want to know what type it is, go look where you declared it, and that's what it is. And most of the modern editor environments, if you just hold your mouse over the name of the variable, it'll pop up a little block that says, oh, this is an integer. It might even tell you what the value that's stored in it is right now. So you can find it out, but reflection is what we use as the term of asking a variable about itself. Sometimes the data is not in the format we want it to be, so we cast it to what we want it to be. And, typecasting is similar to what we say in the movies, even though, Jessica Simpson is a singer, well, we can typecast her in the role of an actress, right, in some movie. What was that? Employee of the Month. Anybody see that movie? I think that's the one that Jessica Simpson was in. Okay, I'm dating myself. So when we do things like what I was talking about before, it's implicit typecasting. We're not saying anything. We're letting the compiler infer the data type. So the data inference rules are applied to the literals, the expressions that we create, and it infers what data type to use when it completes the assignment statement. But when we override it, we're doing explicit typecasting. Our example programs that you've seen, but maybe didn't quite understand fully what it was doing, we've been doing that with getting a string from the input function and casting it as an int to assign it to a variable so we can use it like a number. and we take a variable that contains a number and we want to print it, we cast it back as a string so that we can print it. We've already been doing that a little bit. You've seen a few examples of it, even if you didn't associate it with what we're doing here. So again, this is just terminology for what we've already been doing. And don't worry, either, well, at runtime, you will get an error if you violate the rules, and Python will tell you what you did wrong. Mentioned this already, operator precedence. So when we evaluate these expressions, there's rules for how to do it. And my recommendation is always, when in doubt, put parentheses around stuff. If it's not clear what order to you and you're writing the code, it's not going to be clear to anybody else that reads your code. It's not going to be clear to me as your teacher what you thought was going to happen. So just putting the parentheses around there and being explicit about what order you want things to evaluate is not always a bad thing. So you see that expression there on the screen. What do you think that comes out to be?
And this.
See, I'm going to have to do it in my head too.
Okay.
Okay, I've got the number in my head. Anybody got a guess?
71.
71. I've got one guess over there. Anybody got anything different? Any 14s out there?
29.
Any 29s? Yeah, so it's going to be 71. How do we get that? So parentheses come first. And that's what this PEMDAS acronym is supposed to be helping you to remember. I didn't know this acronym existed, but I saw it somewhere and I thought, ooh, that's cool. I'm going to steal it. So if you just remember for Python, the PEMDAS, parens come first, then exponents, then multiply and divide, then add and subtract. PEMDAS. And that's what order it does it. So you look from left to right. Okay, do I have any parentheses? Okay, yeah, let me do those first. So 6 plus 3 is 9. So you replace that part of the expression with 9. So 9, I don't see any other parentheses. So going left to right, 9 times 6 is 54. 9 divided by 3 is 3. And now all I have left is add and subtract. So 9 minus 3 plus 20. Now, 9 times 6, 54, minus 3 is 51, plus 20 is 71. Okay, we could do that all day. I could print you guys a worksheet and make you do these things. Just hopefully giving you a little bit more respect, be able to figure that kind of stuff out. By the time you get to a point where you've earned a seat in this class, I trust that you've done lots of evaluating expressions in your math class. This is kind of one of those places where programming mimics math, is evaluating these expressions. Yeah, so just to validate it, you can see here, I can just pull up a print statement, print that expression, it says 71.0. Oh, I should have asked you again what data type it's going to be too. But yeah, since it's got a divide in it, the whole thing gets turned into a float. Yeah, so another thing that the book mentions is when we're creating these expressions in our programs, as they start to get more complicated, it's okay to do it in multiple steps, to break up some big, long, complicated expression into individual little operations. That's fine. The only thing it really costs you is having to think of a new variable name, right? So the top one is long, has lots of operations going on, and in your code editor, that's going to be a quite long line of code. But if I break it up, okay, base property price, I have to come up with a name for that value, right? And then I have to break up my expression into sub things, but they're doing the exact same operation, and I couldn't even tell you that one's faster than the other. creating a variable doesn't cost anything really. You know, it depends on how you're using it. Another little trivia thing, I don't come across this that much because I don't really use none much in Python myself. But sometimes variables have no value. Like I can in my Python program over here, I can say variable equals none. Well, let me print variable none. Okay, that might be confusing though. It might not be clear. Because what's the difference between that and saying double quote none? Well, if I look at it now, it's still none. And that's really odd. Why is it still? Yeah, I don't understand that one. I set it to a new value. It should be a different type or a different value. Oh, yeah. No, I get the exact same answer because it doesn't print the double quotes. It takes the double quotes off of the value when I print it. So that could be confusing, right? But let me go back to my first one. Variable equals none. Let me get the type of variable. Now the class, it's a class none type. So the data type of none, no value, is none type. Pretty weird. Versus if I say variable equals double quote none, and I say type variable, now it's a string. So very confusing. But the none keyword is specifically to say this variable doesn't contain a value. I don't know how often that will be useful for you, but it's something that you need to know. And comparing that to other languages, some languages don't even let you create a variable without initializing it. Now, you'll see that in a couple of different flavors. Some languages will let you declare a variable, but not give it a value, and then say, well, that's fine. But if you ever try to use it in that state, that's what I'm going to get you. I'm going to say, sorry, but you tried to reference memory that hasn't been initialized yet. Other ones, you have to initialize it, and if you don't tell it what to initialize it to, it'll be automatically set to a default value. C++ is like that. If you declare an integer value in C++, it's set to 0 for you, even if you didn't set it to 0. I always tell people to be explicit about it, just so you're in control and you know what it was set to. But it's going to have a value. Back when I was early in my career, I was working at American Airlines, and we were developing a CD-based travel application where a travel agent could let you sit down there and they would pull up can you believe it, an actual map and put little dots on it where the hotels were. Yeah, I know. That's Google Maps does that every day. But back then, that was brand new and nobody had that, and we were inventing it, and it was pretty cool. But at the time, we had this debate in our team whether to use Borland C++ or Microsoft C++. And that was one of the differences between the two, is in Borland C++, if you declared a variable, they didn't automatically initialize it, and Microsoft did. And the benefit that was touted there was that that will keep you from accidentally, the Borland compiler, it was Wild Wild West, and you had very few guardrails, and they were claiming that that made it faster. And back then CPUs weren't very powerful, so you were trying to eke every little CPU cycle out of it you could. But that was one of the differences between those two compilers back then. But now all modern compilers have gone the way of the Microsoft way, and Borland is out of business. So now C++ is generally thought to automatically initialize all variables to a default value when you declare them. but Python makes you initialize them. You won't know, I mean, you know, it's like you could declare a variable and not set it to a value. But how would you know? Because the first time you try to reference it, it's going to say it doesn't have anything in it. So what's the point? You might as well just say, hey, here's my variable and I'm setting it to a value. Okay, backing up a step further, Python doesn't require you to declare your variables, right? So how would that ever even come up? But I still recommend it's good form to think about your design, you know, kind of like the Flowgorithm way. Flowgorithm makes you declare your variables at the beginning. That's what I would do. At the beginning of your Python program, I would say, hey, here's my variables and I'm initializing each one of them to the default value I want them to have. Great, now I'm organized. There's all my variables. And then I'm going to go on and write my code below that. It's perfectly fine to do. And it's actually a pretty good programming style. Enough about that. Okay, we already talked about this, reassigning, you know, you can assign a value to it, assign a different value and see that it changed. I already kind of used that example, showed you already how that works. You know, set it to a string, so type string, set it to a number, it changes to type int. Now I'm going to talk for a minute about your prompt messages. So in Python, we have been doing input statements to get our data, our input data from the user. And we've been doing it the second way. Well, you can do it two different ways, is what this example is showing you. You can do it the second way where you give it the prompt message inside the input function call, and it will display that and wait for the user to type something and hit the enter key, and then it'll come back and put the value into your variable. That's perfectly fine. Or you can do a print statement and print your prompt message and then say variable name equals input with no prompt message, and it does the same thing. Right? Those two are functionally equivalent. Why would you do one over the other? Maybe you've got a really long prompt message that you want to display, and you don't want to have a huge long line of code in your editor. You know, you want to break it up just like that previous example. Perfectly fine, it's your choice. This is where a lot of this comes down to programming style, where I talked about, you know, programming being a creative exercise. You know, the text editor is your canvas and your Picasso, and you're creating something artistic. And you get to choose what your prompt messages are. You get to choose what programming style, your variable naming, within reason. I may have feedback for you, but hey, you get to choose. And in the end, as long as the program runs and produces the correct output, then you're good. Next thing is these \n characters. So you can, if you study the code up there, hopefully you can see it. I've got a really long prompt message, and I put these little \n characters in the middle of it where I want it to print a little bit and then drop to the next line and print some more and drop to the next line and print some more. So I can create a multiple line print message by making one big long string with those little \n in it. Okay. So just like I can print that way, I can also do that on my input statement if I want to. The second example, you know, it's a very long descriptive prompt message. Think about how many chickens you have, \n. The number of red ones, the number of white ones, \n. All of them, \n. How many do you have? Right, you can do that. And it'll print lots of different stuff on the screen, whatever you want. I also kind of showed a different technique for breaking your code up. These little backslashes at the end of the line, if you put a backslash at the end of your line, that tells Python, I'm not done yet. I'm going to continue this line of code on the next slide. You got to be kind of careful where you put the backslashes. Like I didn't have the guts to put the backslash in the middle of one of my strings. So I just stopped my string and put a plus sign and a new string on the next line so I concatenate them together. But, you know, have fun with that. Why would I do it? Better readability and maintainability. You know, the 5 minutes while I was writing that code, it was my opinion that this made the code more readable, right? That's all. Okay, moving on. Boolean. So what is this Boolean stuff? And you ask what float is. Float's decimal data. What's this Boolean stuff? Boolean is all about the true and false. It was created by this guy named Charles Boole back in the mid-1800s. The last time I checked, we didn't have any computers back then, except the ones that the aliens brought back to help the Egyptians build the pyramids. Those don't count. Boole didn't know about those. He had his head in the sand. But Boolean logic is a branch of mathematics that deals with yes, no, true, false decision-making logic, and it has existed for a long time. There's all these rules, and, or, not, exclusive, or, all that stuff was developed long, long ago. So there's these keywords that we have, true and false. So true is true, naturally. False is false, naturally. Not true is false. And not false is true. Well, that sounds pretty obvious, right? Again, let me give you a page and a half of questions about Boolean logic on a piece of paper, and we'll see how quickly it gets more clarity. In Python, you can evaluate values, literals and expressions, whatever. You can evaluate them as if they were a Boolean, and it gets kind of weird. The empty string is the only string that is considered false. But anything that has character data in it, any string that actually contains something, is considered to be true. I know, kind of weird, right? Similarly, when we talk about the numbers, 0 or in a float 0.0, that's considered false, and any other value in those types is considered to be a true value. So if you wanted to use, I don't know, strings and decimals in Boolean logic expressions, you can, and Python will try to infer what the heck you were thinking when you did that. So then at the bottom, that last line, I have an expression, 1.5 and 0 or cat. That is an expression, and it evaluates to true. So there you go. Okay, more terminology, or I guess repeating the terminology. So I mentioned this before, mutable versus immutable. So mutable is a fancy word for it can be changed. Immutable is the opposite, it can't be changed. We talked about constants, and they were talking about constant literals. Python doesn't really have constants. Anything that you declare can be changed, it's all mutable. So if I define a variable called pi, and I set it to 3.14, and then later in my code, I set it to 17, and then people start trying to get the area of a circle with using my definition of pi, we're going to get some interesting results. But there's nothing that keeps you from doing that kind of thing in Python. It's kind of interesting. But what they tell you is with your naming convention, if you declare some variable and you intend for it to not be changed willy-nilly all over the place, just make it uppercase. It has no bearing on whether it's changeable or not, but at least we're telling each other, hey, I meant for this variable to be a constant. So capital P, capital I, if I use that as a variable name and I put 3.14 in it, I'm telling everybody else, hey, don't assign this to a different value. This is supposed to be constant. Yeah, there's this other language, F sharp. Has anybody heard of that? It's a weird language. They call it a functional language. You'll have to Google it and read about it. You can kind of get in the weeds real quick though, so be careful. A lot of it's marketing and hype and stuff like that about it. I haven't found much use for it, but in languages like F sharp, everything is immutable. If you declare something, it's got that value forever. You can never change it. You can create a new thing and put a different value in the new thing, but you can't change the value in things that already exist. They're completely immutable for weird esoteric science, computer science reasons. But anyway, there it is. Okay, something useful for you. Has anybody read in the book and heard or come across the term sentinel value yet? Okay, well, they will. You can Google it, find out what sentinel value means too, get more information. But you can think of a sentinel as just like a landmark, something that when you come across it again, you'll recognize it. And in programming, we're going to talk about sentinel values, usually to control a piece of code that we want to repeat. And we're going to repeat that code over and over and over again until we check some variable and it has a sentinel value in it. Like, do you want to do this again? Yes or no? And if you enter no, okay, well, no is my sentinel value. Whenever I see no in that variable, I'm going to quit and I'm not going to repeat anymore. And we'll get into loops, 2 or 3 weeks from now. But for now, for a little while, you're going to have to just do what I do and just follow the leader until we get there. Here is an example, one example of a program that uses a sentinel value. So it's kind of a weird statement. Said while is how we do loops. We'll learn about that. And we say while true. Well, that's weird. So essentially we're saying while forever. Keep looping forever. Another thing about Python is anytime we indent the code, we've created a new block of code. Python is all about the indentation. So all of this stuff that's indented, the rest of the program is going to be repeated inside this loop. We would put our code here. So if I tell you, hey, go ask the user to enter 2 numbers, add them together and print the result, that would all go right here. At the end, you would come down at the bottom and you would indent all that, by the way. And then at the bottom, you would just type all this stuff in there. And you can see what it's intending to do. Press enter to continue or X to quit. So instead of yes or no, I'm saying either nothing or X if they want to quit. So here, X is my sentinel value, right? So right after that, I say, if the variable keep going contains character X, then break. So when I hit the break statement, it's out and stops repeating, ends the program, and we're done. But if I run this program, it comes in here and it processes your code, executes your code, comes down here, hits this, and we display that message, and they hit enter. We'll come right back up here and we'll do that again. Come right back up and do it again. Come right back up and do it again until the user gets that prompt and they hit X and enter, and then it will exit. So that's one pattern. It's like the first programming pattern I'm showing you that you just kind of need to remember. And you will use that over and over and over again, even though the code that goes right in this part is going to be completely different depending on what the assignment is. So if you see me give you an assignment, it says, keep asking the user if they want to do it again until a sentinel value is entered. That's the kind of pattern. And you don't have to do X to quit. You can do whatever you want to do. It's up to you, but that's the pattern that you're going to follow. Some people find that whole loop forever and then break at the end pattern kind of awkward. So here's another pattern. I'm kind of one of those people. This pattern makes me feel a lot less itchy. You know, I get this itchy in my back of my brain when I do the previous one. This one just is more satisfying to my anal retentive brain. So what I do at the beginning is I set a variable equal to true. Then I say while that variable is true. Again, here's the part where you would put all your code indented. And then at the end, I say, now just go get another value for keep going. And as long as I enter something that is true, if I enter cat or 17 or 42.5 or whatever I enter there, it just has to cause keep going to evaluate the true, right? Then it'll keep repeating. But if I ever hit X, then what's going to happen? Actually, this has got a bug, doesn't it? Okay, so I make bugs too. So let me destroy this very expensive thing by writing equals true on here, because that's what that should say. Anyway, that's those two patterns do exactly the same thing. This one and that one. Except, like I said, this is supposed to say, well, keep going. It's supposed to say, well, keep going is not equal to X, not equal to my sentinel value. So I just screwed up. My bad. So how many people like that pattern, first pattern? How many people like the second pattern? Hold up one finger or two fingers. Okay, good mix. That's about what I would expect. No wrong answer. As long as it works. Okay, some more good programming habits. So we've talked about this last time for this chapter. This is kind of summarizing as we wrap this up. So if all of us as programmers learn to take a breath once we've read the assignment and make a plan for our algorithm instead of just jumping in and starting your code. If we stick to the habit of making pseudocode and flowcharts. Now, I'm not going to blow sunshine at you up here. Do I make a flowchart and pseudocode for every single program? No, I don't. But they do come in handy. Usually when I stop and I do pseudocode or I stop and do a flowchart is when I'm working in a team of other developers and there's part of the code that's really complicated and we're trying to communicate to each other how that piece of the code works. Or if I'm given a bug to fix and I sit down with this really complicated piece of code and I have to figure out where the bug is, then I might make some pseudocode as a summary, as an outline of what that code's doing and how it works, so I can understand it better. I'm communicating the design to myself in that case. But after 40 years of doing this in 8 different programming languages, no, I dream in C++, so I don't have to do that anymore. You know, more power to you if you get to that point too. But it's a true statement to say programs would be better if developers stopped and took a moment and thought about their design and did some preliminary notes about it before they jump in. After you've got it coded, you can desk check it, or like Flowgorithm lets you step through your logic before you even pull up a code editor. That's great. Use good variable names, and later when we're creating functions and stuff, you know, use good function names for stuff to make your code readable and maintainable. Comments, you know, putting comments in your code appropriately. I think you see the level of comments that I put into my code with these patterns. I consider it sort of a, you'll find your voice in how you write your comments, but I assume that somebody like me is sitting at the table next to me and I'm explaining them, here's what this line of code does. And what it actually ends up being is, I'm writing these comments for future me 3 months from now, when I come back and read this code and think, what the heck? Man, I must have needed more caffeine when I wrote this code. What was I thinking? So that's the level of detail or the voice that I use when I'm writing my comments. They're easy to put in there. It saves you a lot later when you're trying to understand what you wrote. And then when you're doing your prompt messages, use good prompt messages. You know, tell the user clearly what it is that you want them to do. I'll give you a little bit more detail on this. Here's an example that has a whole bunch of different parts to it. But I just think it's kind of cool. When I first start a new program, I'll put this little heading line at the top. Doesn't mean anything to the correctness of the logic of the program, but I give my program a name. I say this is version 1.0. I put this little copyright line in there, which nobody's going to care about but me ever. And you know, just when I started writing programs, I just got into the habit of doing that. Copy and paste it to every program that I write. And that's like my little hello world template. We've got our little loop here. We've got instructions for the user. We've got good comments sprinkled throughout. I've got very nicely worded and formatted prompts without misspellings or typos or grammar issues. And, you know, when I print my output, it's formatted well. And, you know, I don't just at the end say print variable. I say print your answer is and the variable, right? So all of those things go into making just a plain old program look a little bit more professional, a little bit more polished. And again, my assumption is if you're going to go on and do more programming after this, you're going to want to start mimicking these habits, because you start putting these things into your portfolio or in your GitHub account, and later referring back to this and showing people, hey, yes, I can program in Python. Here's some examples of the kind of Python that I can create. You're going to want it to look official. You're not going to want to spend a weekend going back and editing all of your GitHub repositories to clean them up so they don't look crappy. So, you know, it's like, you know, leaving your room a mess and then inviting people over kind of thing. So anyway, for what it's worth. This is the same thing with the other pattern, so that you've got that example. And that's it. Any questions? Okay, let me see if I can pull up. I'm still logged in. Yeah, so we're in module 2 still. I've got the lecture up there for the 2 modules, and then this will go in there as the 3rd one. We've got the discretionary spending project. Hopefully everybody's working on that. It's due September 13th. Got a discussion assignment out there for variable naming to just, you know, share your thoughts. I'm curious what you think about it. And then the quiz for chapter 2 is out there. And that's due day after tomorrow. Yeah, so you got the discussion and the quiz that are due Friday, and then the programming assignment is due the following Friday. Okay.
I have a question.
Yes.
On the ebooks, when I go into the ebook, I open it up, and in there, you can see the chapter, right? You can see the chapters. But if you open up on the right side on that banner, if you open up the full book, the chapters don't match. I don't understand why.
Well, don't get confused between modules and chapters and units and all that kind of stuff. We are on chapter 2, elements of high quality programs.
So that's what we should be reading, not not the full book on the right side.
Are you saying that that's different?
Yes.
That would be weird. Table of contents. So it says 2 elements of high quality programs. Yeah, all of this stuff in here, that all looks familiar.
But if you open that on the left side, it doesn't. It's not the same.
Well, see, I'm not really using any of this mind tap stuff in here this semester. All of our stuff is in Canvas.
Yes,
So
so what side do we use then? The left side or the right side?
the right side,
The full book.
yeah. And then I can click this and say go full screen, and so that now that's all you see.
So then don't use the left side, because you just said
Yeah.
to use the left side.
Yeah, the left side is nothing. All that stuff except for the book is hidden.
Because on the right side, it's introductions to like hardware, software, on the first chapter. And that's not what we're learning here. That's why I'm confused about what I'm supposed to be reading.
Yeah, I mean, I did a little bit of an overview of chapter 1, but we're past that now.
Right, but even chapter 2 is the same thing. That's what I don't know what to read.
I don't know.
The full book or on the left side?
Full book, chapter 2. So at this point, we've covered chapter 1, an overview of computers and programming, and chapter 2, elements of high quality programs. That's it. We're not to the, chapter 3 is, they stuffed a whole bunch of stuff into chapter 3, 4, and 5, and 6. I mean, it's gonna go pretty downhill if we follow the pace of the book. We're gonna take our time and get through those and do some assignments where we get to reinforce those concepts, because though that's where all the meat is. By the end of the semester, I would like to get to file handling. We probably won't even cover any of this other stuff. Chapters 8 through 12, we probably won't even go into those. I'll leave that for your next programming language class, where you get into all that kind of stuff. So this semester, our goal is to get through chapters 1 through 7.
So work on the full book, right? Full
Yeah.
book, the full book.
Yeah, I don't see any of the other mismatched stuff that you're talking about, but yeah, if I saw anything, like over here on the left, chapter 1, an overview of computers, chapter 2, elements of high quality programs, that's the 2 chapters.
Yeah, it says that, but once you go inside of it, you go read it, it's not the same.
Yeah, he's talking about the chapter 2 Python BAL guide.
Yeah,
Oh, well, that's supplementary information. I mean, it's okay if you want to watch that and learn about it, but that's not stuff that I'm covering.
all right, well, that's what I want to know. What we're covering on the right side of the full book. That's what you want us to read.
Yeah.
Okay.
And what is this? Yeah, guy.
Because it has the same titles, but once you go inside of it, it's not the same one.
Okay, I see what you're confused by. Yeah, consider that supplemental material.
Because they're all saying chapter 1, and so I'm like, wait a minute. Is it 2 books or is it the same book?
Yeah, I didn't put any of that in the reading, so you don't have to read that.
All right, so just stick with the full book here. So.
Yeah.
All right.
Good question. Thanks for pointing that out. Okay, that's all I had.